welcome to the lecture of Professor Nicolai from Potsdam. He was friendly enough to give a lecture series on quantum field theory, an introductory course. Two things in the beginning. First, tomorrow's lecture will be in a different room. I think it's a council room, I was told. And second, there will be a questionnaire. Everybody is supposed to fill it out. Yeah, it will be here on this table after the talk. And to give an incentive, everybody who fills this out can receive transparencies of the lectures. And for this to work, you must fill in your name on this sticker on top of this page. So please come down afterwards and pick up these pages. Okay.
Achso, sollen die jetzt ausgeteilt werden?
Nee, die wollen die Leute holen und machen.
Ja, dann sagst du es ja nicht gleich. Achso. Ah. So, welcome to these lectures on quantum field theory. Let me first say something about the mode of presentation. I'm going to work on the blackboard, and I will not use transparency, so maybe you would move up closer a little bit. And on this is the only transparency. It wasn't even prepared by me. It was prepared here by the division. Shows you the content, or the intended content of these lectures. I intend this to be as pedagogical as possible, and I would like you to ask questions whenever they arise. So if you have questions on my lectures, please don't wait until the end. Please ask them right away. As I said, as it is said here, the emphasis will be more on general principles than on specific applications. There's always a choice. In teaching such a course, I could just as well have started with or moved on to things like how to calculate cross sections and so on. I have chosen to dwell a little more in the basic principles of quantum field theory, and there's now the table of contents. I'll start out with a short section on basic principles. It should be plural, not singular, because unfortunately not that far that we can reduce everything to a single principle. There are few principles that go into the formulation of quantum field theory, and that I will recall. Then we'll move on to the representation theory of the Poincaré group. It's a very basic chapter. That's where you will learn how theorists define what an elementary particle is. And then I will move on to the free scalar field and the free Dirac field. These are the prototype or the basic models of quantum field theory, and you can think of these models as just being some infinite dimensional generalization of the harmonic oscillator that you have encountered in quantum mechanics. After this, of course, we will have to talk about interactions. And here I will tell you a little bit about, first of all, about the classical aspects, meaning I will have to tell you on how do we move from a free field theory to an interacting field theory, and what are the difficulties there. And I will also tell you a little bit about the principles. There are things like symmetry principles that go into the construction of field theories. And symmetry principles have become very important over the last decades in quantum field theory, as you know. Much of it can be reduced to the question of what is the right symmetry of nature. And therefore, in order to make this not just a standard course of quantum field theory, but also tell you a little bit something that you cannot find in all the books on the subject, I also decided to tell you a little bit about supersymmetry, basic principles, and a little bit how to go about constructing models. And finally, I will tell you about how to construct S matrices and where to go from there, because these are, of course, the quantities that one has to compute and are really relevant for what's being done here at CERN in the experimental labs. As I said, the emphasis will be more on general concepts than on specific applications, and for most of this lecture, all I will assume is the knowledge of special relativity and quantum mechanics. So let me now start. Basic principles. First of all, what is quantum field theory? So this is chapter 1, basic principles. So the first question is, what is quantum field theory? So, or relativistic quantum field theory, I should say. Relativistic quantum field theory. Well, I will abbreviate this with QFT or RQFT, is the unification of, or relativistic quantum field theory unifies quantum mechanics with a special relativity and special relativity. Quantum mechanics has its fundamental constant, which is just a Planck constant, h bar. And special relativity, of course, has its own fundamental constant, which is the speed of light. And perhaps you know there's a third fundamental constant, or which is considered fundamental nowadays, which is the Newton constant of gravitation. This will play no role in these lectures. Now, for most of the lectures, we will put h bar equal to z equal to 0. That corresponds to the choice of units, and this is simply in order to make the equations less cumbersome. Well, basic principles. There's not just one, as I said, but there are several. And of course, the first principle that goes into relativistic quantum field theory is requirement of relativistic invariance. I assume that you know about this, so this is also a little bit to set up my notation and conventions. As a theorist, I can assure you that 90% of the work that a theorist does is accomplished once you get clear about your notations and conventions. From there on, most of the time, things are pretty straightforward. So, we live in a four-dimensional space which is parameterized by coordinates x mu, ct, and x, and the derivatives with respect to these coordinates will be denoted by d mu, and we will be considering Lorentz transformations and translations. So we'll look at the following transformations. X mu goes into x prime mu. There are two kinds of transformations here. First of all, there's a translation. And secondly, there's so-called Lorentz transformation. This we will write as follows. And these transformations, this is the way we write the Lorentz transformations. We use the summation convention. And here we have a 4-vector describing translations or parameterizing translations in space and time. And these two things together make up what's called the Poincaré group. So the Poincaré group is, by definition, the combination of translations plus Lorentz transformations. And these Lorentz transformations are defined in such a way that they leave invariant the relativistic metric or Minkowski metric, which is defined as follows: x mu is equal to x mu, eta mu nu. The so-called Minkowski metric, eta mu nu. This is the diagonal matrix, which has these entries here. And if you now require that x prime squared, well, put a equal to 0, we look at x prime, goes into lambda mu nu x nu, and we require this relativistic scalar product to be invariant, then it follows that we get the following relation, lambda mu rho, lambda nu sigma, eta rho sigma should be the same as eta mu nu. So this is almost like orthogonal rotation, definition of orthogonal matrices, except that you have these different signs here, and that's why the group, the Lorentz group, is also called SO1, 3. So, a relativistic quantum field theory must respect this invariance, which means that whatever we calculate in relativistic quantum field theory, vacuum expectation values of field operators, field equations, quantized field equations, must respect Poincaré invariance, in the sense that will be made a little more precise later. So whatever we calculate, it must respect this invariance. By the way, this is something I forgot to say. I have my handwritten notes here, and eventually we can distribute copies of my handwritten notes. I'm still polishing them a little bit, weeding out mistakes here and there, and trying to make things as clear as possible. I also have, I hope, a rather legible handwriting, so you can. So eventually you will have copies of this if you want. So this is the first principle. The second fundamental principle is of relativistic quantum field theory is that of causality. Causality. Now, you all know that if you define a relativistic scalar product, you can take 4 space, so you have time here, and the space coordinate here. Then you can draw a light cone in this space, which goes like this. And then we can distinguish according to whether vectors are time-like. Time-like vectors you get when x squared is positive. And the time-like vectors are all the ones that are within the light cone. Then we have light-like vectors for now. Or sometimes this is called null. And finally we have space-like, which means that the relativistic distance is negative. And now the causality principle in classical special relativity tells us that there's no motion at speed greater than the speed of light. So that means that if you have a particle that moves in this space, it must move in such a way that its tangent is always then upward. It always so motion is always such that only motion with x dot is less or equal to 1 is allowed. Now that means that, of course, this path can wiggle as much as it likes, but what it really means is that at each point of this path, which I'll draw here once more, when you draw a little light cone around any given point, it just means that at each point the motion should be within this forward light cone. Of course, motion is always upwards, forward in time. But so you can draw a little light cone at everywhere in Minkowski space, and when you have a motion of a particle, then it must, at each point, it must be such that it moves through this, it always stays within the light cone. Now this is the causality principle of classical special relativity. Now in quantum field theory, it will have to be, it's a little more sophisticated, because in quantum field theory, we'll be dealing with objects called field operators, and we'll see examples of them. So field operator is something that generalizes the basis of quantum field theory. It's something that generalizes the operators of quantum mechanics. As you know, in quantum mechanics, classical variables, numbers become operators. Now here, these things, in quantum field theory, you deal with operators that depend on the space-time points. So generally we'll be dealing with objects like with fields, phi of x, but where the field is no longer a classical field, but an operator in some Hilbert space. And then the causality principle tells us that two such field operators should commute at space-like distances. If x minus y squared less than 0. So that's the generalization in quantum field theory of the classical statement that there's no action, that action cannot propagate at speeds greater than that of light. And this is something one will find time and again, and in the case of the scalar quantum field, we'll be able to verify this very explicitly. And as I said, this is something that holds very generally. It also holds for vector fields. Of course, when we deal with spinor fields, we have to replace commutators by anti-commutators. But basically, this is what the principle tells us. Well, a related principle to this is that of locality. What is locality? Or sometimes quantum field theory in the more axiomatic setting is also called local quantum field theory. Basically what it means is that the following interactions are point-like, or when we talk about the fundamental Lagrangian, it means that there are no form factors in fundamental Lagrangians. This will be explained in a little more detail later. So as you know, there are particles which we now consider as fundamental in the framework of quantum field theory. So fundamental particles. Like the electron, quarks, etc., others, which we consider as fundamental, are treated as point-like, in the sense that the way in which they enter the description of quantum field theory is really in this in this scheme of quantum field theory, we treat these particles and their fields really as mathematical points. Of course, there are lots of other elementary particles like proton, neutron, mesons, and what have you. But these particles are not considered fundamental, as we know, but they are considered as composite. So we'll try to reduce the theory to the fundamental particles and a so-called standard model of elementary particle interactions based on SU3 plus SU2 plus U1. That contains just the particles which we consider as fundamental. And then, of course, the theory has to tell you why it is that these particles, quarks, etc., combine into the particles that are seen here in the experiments. Well, this is of course what we see, but on the other hand, it has there's a mathematical consequence of this, and this has to do with the fact that this will imply so-called short distance singularities. Of course, when you have objects that live on mathematical points, like these quantum fields, you have an operator for each point in space-time. To each point in space-time, we assign an operator. Then one must watch out for singularities of the following type. For example, if phi of x is some operator, then in general, you cannot just, like in the classical theory, you cannot just take the operator, square it, and claim that this is an operator again. What will happen is that this object will no longer exist in general. So it may not exist as an operator. This is a little bit like when you take the delta function, delta of x, you may remember that you're not allowed to take the square of a delta function. That gives you something which is too singular. Now, in quantum field theory, one runs into this kind of problem all the time, and of course one has to invent a way of how to solve these difficulties, and roughly speaking, this is the reason you have to modify the theories and introduce a procedure which is called renormalization. So renormalization is a necessity in quantum field theory because these objects you're dealing with are very singular, and there are so many of them. This kind of problem does not arise in ordinary quantum mechanics. It arises here because we have a sort of continuous infinity of objects, one at each space-time point, and these objects can be quite singular. Now, of course, you might ask, well, what happens if I go to smaller and smaller and smaller and smaller distances? At some point, maybe space-time dissolves or something else happens. We've seen this before in physics, that if you go to smaller length scales or larger energy scales, that some theory gets replaced by another. And this may, of course, also be true with quantum field theory. But at the moment, as far as we know, and as far as it's been tested, it works down to distances of 10 to the minus 18 centimeters or so. Okay. Now, there's another feature. It's not a basic principle, really, but it's a basic feature of quantum field theory, namely the following. These theories are always multi-particle theories. Meaning, whereas in quantum mechanics, you deal with one particle at a time, think about the hydrogen atom and the electron. In this case, you have a theory that allows for the creation as destruction of or annihilation of particles. So create and annihilate particles. And annihilate particles. Of course, you will say this is obvious, and of course it's obvious once you live here at CERN, look at what happens in the experiments, because particles are constantly created and annihilated, and you would not be a theory that wouldn't have the capacity to describe such processes would be no good. But what I want to say here, it's not just an empirical requirement put in from the outside, but it's built into this whole framework. By the way, I should also say there's, of course, also something called non-relativistic quantum field theory. This is when you leave out the relativistic, and this is relevant, say, for solid-state physics. But relativistic quantum field theory, when I talk about quantum field theory, I always mean that we put these two things together. So there are now two ways of doing a quantum field theory, at least. They're the more phenomenologically oriented people, and the more rigorous people. And well, first, maybe I should say a few words about rigorous result. I've described these principles. You can axiomatize these principles, and you can now ask whether you can really mathematically construct such theories, that they would be such that any mathematician would accept this as a correct definition of a theory. Now, as it happens, this is quite complicated, and when you really look closely, and this has been, people have been thinking about this for the last 40 years, trying to really write down a quantum field theory, a non-trivial quantum field theory with interactions, and really establish as mathematical theory, it has turned out that it's very, very difficult. Mainly because of these problems. And to this date, there's not a single example of a quantum field theory in 4 dimensions that interacts, is non-trivial, has non-trivial S matrix, and can be shown to exist. Rather, what we do is since we can't solve the theories exactly, we start from the free theory, which is much of these lectures will be devoted to free theories, and then we perturb, and then we develop things like Feynman graph expansions and so on, and we get something called perturbation series, which has to be renormalized. Every term has to be renormalized to deal with these singularities. But then the question, of course, arises, well, can we sum this perturbation series? And there are indications that even if you do the renormalization in the Feynman graph perturbation expansion, that the sum at the end of the day will not converge. Such is, for example, the case for quantum electrodynamics, where there claims that the theory will start diverging at order 130 or something like that. Now, so there's a little bit of unease. We have a theory that, it should be said, works spectacularly well for the description of fundamental interactions. We all know about the QED, the G-2 result, and more recently the calculations of process in the standard model, where the standard model is being tested to 1 and 2 loops, and it works exceedingly well. So we have this a spectacularly successful theory, but when you look closely, it turns out it's not a theory really at all. It's a cookbook recipe in some sense. And these are there are now two ways to approach the subject. There are some people that say we don't have to worry about all these mathematical things. We just take quantum field theory as a cookbook recipe that tells us how to calculate amplitudes, how to calculate cross sections, decay rates, and so on, and then compare with this experiment, and that works nicely. And there are some people that say that that's all there is to this theory. On the other hand, you would say, well, maybe I would still feel a little better if I knew that there was at least one single non-trivial example where all these nice principles, which can be axiomatized, can be checked and verified. So this was something that people would have worried a lot about 20 years ago, but nowadays the point of view has changed a little bit, because we now believe that relativistic quantum field theory will be supplanted by something else eventually. Just like classical mechanics was replaced by quantum mechanics when we go to very short distances, we all believe that the quantum field theory, relativistic quantum field theory, will be dissolved or replaced by something else once you go to very, very, very small distances, even much smaller than ones that can be tested nowadays. And the reason, of course, is that if you really want to unify things, you also have to, you cannot neglect the third fundamental constant, which is Newton's constant, and that will then lead us to some kind of theory of quantum gravity. So the attitude nowadays is that we no longer worry about the fact that there are no, people haven't come up with non-trivial examples of interacting quantum field theory in 4 dimensions. We simply say that these theories, like the Standard Model, are very likely just some kind of, in some suitable sense, low energy approximations, effective theory approximations to some other theory that will be seen at yet lower distances. So this concludes what I wanted to say about basic principles. Do you have any questions? Well, this level of generality, probably there are not that many questions one can ask. By the way, should I stay in the middle of this? Should I just use the middle blackboard, or are you happy if I also use this one and that one? Doesn't matter. Okay. So another thing I forgot to tell you is that on this note, in these copies of my notes on the title page, I've also given a few references, books on quantum field theory, and of course you should understand this lecture course really as only as some kind of appetizer, and then once you really want to get into things, you look at one of these books. So chapter 2, representation theory of the Poincaré group. Well, I've already mentioned the Poincaré group, and nowadays with our understanding of symmetries, we believe that this is at least the core part of the theory, so that rather than starting with a scalar or Dirac field right away, I want to tell you a little bit about the general principles, because the analysis of the Poincaré group and its representations will tell us what are the possibilities for particles, what kind of representations, what kind of particles can you generally have in quantum field theory. And this is, of course, well, another way to say this is the following. When in an exam, professor asks you what is an elementary particle, how do you find the notion of elementary particle, then the answer many professors would like to hear is that you say an elementary particle is by definition a unitary, irreducible representation of the Poincaré group. So the Poincaré group is, of course, this thing here, as I said, and we're not talking about the representations. Let me say this once more. This is, by the way, also a point of view. If you look at, there's a very recent book by Steven Weinberg, or really 2-volume book on quantum field theory, where he also takes this point of view, whereas in the older books, this is something that comes a little later, but in Weinberg's book, this is also taken as a fundamental or good starting point to discuss quantum field theory. So here we said once more, an elementary particle is unitary, irreducible representation of the Poincaré group. Or maybe I should introduce a letter for this, because otherwise I will be writing so much. So let me call it script P. So, script P is the Poincaré group. Now, why do we insist on unitary? Of course, that's quantum mechanics. We have a Hilbert space, and we also remember that how it works for angular momentum. There as well, we have well, first of all, you start by writing down the angular momentum operators. First of all, an orbital angular momentum operators. Say when you try to solve the hydrogen atom. And then afterwards, you realize that you can abstract from this. You take the commutation relations of the angular momentum operators, and then you abstractly try to analyze the representations that can occur. And then you find, as you know, that the representations can be labeled by something called total spin, which can assume values 0, 1/2, 1, half integer values. And then the component of the angular momentum, the eigenvalue of the angular momentum operator along the z-axis. And we want to repeat this exercise here. Now there's one important difference here, and between the analysis for the rotation group, which you all know, and the Poincaré group, and that is that the Poincaré group, or Lorentz group, is what's called non-compact. And that means that, and that implies there's a theorem that says that there are no finite-dimensional unitary representations of non-compact groups. Non-compact groups, and that means that we will be led to infinite dimensional representations right away. Non-compact groups. That means we will have to deal with infinite dimensional representations. So while for SO3, which is a compact group, the multiplets, spin multiplets for any given spin are finite dimensional. Here in this case we'll encounter infinite dimensional representations. Well, now I have to explain this in a little more detail. So once more we're looking at, first of all we look at representations which are, or we look at transformations which map x mu to x mu prime is a mu plus lambda mu mu x mu. I'll state it once more. And each such representation will be, each such transformation will be represented by a unitary operator. Each transformation will be represented by some unitary operator. You all know what unitary means. It means u dagger is equal to u to the minus 1 operator. U, let's call it u. And of course I have to put a label because you have these transformation parameters. So this thing will depend on the translation parameter A and the Lorentz rotation matrix lambda. So for each pair of A and lambda, we will have a unitary operator acting on some, in this case, infinite dimensional Hilbert space. So this construction goes like the construction of representations of the rotation group in ordinary quantum mechanics. We will try to represent the operators. First of all, the translation operators. So we'll write this as u of a as exponentials of I times a mu times some generator of translations, where the P mu are the generator momentum operator, a generator of translations. So P mu, we have 4 of them, splits into P0. Well, this is just the Hamiltonian and the momentum operator proper. So this is the Hamiltonian of the theory, and this is the momentum operator. And you see the nice thing about this kind of analysis, and the reason why it belongs at the beginning of the lectures and not somewhere in the middle, is that we can do this analysis without knowing anything about what this Hamiltonian is. We don't have to specify any Hamiltonian. All we will need is the commutation relations, the general commutation relations of these operators. We need not know what the specific model is under consideration. Of course, there are specific models where you can construct specific expressions for these Hamiltonian translation operators, but at this stage and for this analysis, we do not need these explicit expressions. So, to repeat, U will be written as the exponential of some translation operator, and I have to go to the... And of course, we also need generators for the rotation and the Lorentz boosts. And then it almost works like in ordinary quantum mechanics. So, I forgot to say that in order for this to be unitary, of course, we have to assume that this operator is Hermitian operators. Which means that P mu equals P mu dagger, where the dagger is, of course, defined with respect to this, whatever the norm is on the Hilbert space. This is, again, something we don't have to specify. And this then ensures that the eigenvalues of these operators will be real, as they should. So, we have one set of operators generating translations, and this is something you know from quantum mechanics already, because we have the translation generator generating translations, and the Hamiltonian operator just generates time translations, or in other words, the time evolution of the system in question. And the new thing here is just that we really put them together, combine them into a 4-vector. So, that's the easy part of the Poincaré group, and the more complicated part is connected to to 0 lambda, which I will simply abbreviate as U of lambda. And this will be written as exponential of I over 2 times, well, that's the infinitesimal parameter for the Lorentz transformation. Well, it need not be infinitesimal, times a set of generators, which are the generators for the Lorentz group, where M and U are the Lorentz generators. And again, we assume that these generators are Hermitian with mu nu equals mu nu dagger. So again, I can make this split into 1 plus 3 time components and space components. And here it's a little more complicated because these things are, as I should say, this pair of indices, these generators are antisymmetric in these index pairs. So there are how many of them? Well, there are 6 of them. And we can split them as follows. if we take mij, where these indices ij run only over 1, 2, 3, with ij, then these are just the angular momentum, standard angular momentum operators in a notation where m12 is equal to j3. Now here I have to be a little, I think I've glossed over a little bit of, but it doesn't really matter. We say that m12, whether I put the indices upstairs or downstairs, here doesn't really matter. We define j3 as m12, m23 as j1, and m31 as j2. And then these are just the angular momentum operators. And then, so these are the first three, and then there's a second set where one of the indices is equal to 0, and these are the generators of Lorentz boosts. Or Lorentz boosts. Yeah. Now, the next question is of course, an important thing now, is what are the commutation relations obeyed by these quantities. Now, for the translations, you can already say what it is, because translations commute, therefore the generators will also commute. So that's easy. We have P mu with P mu is equal to 0. So if you put mu equal to 0 and nu equal to I, that of course simply means that the momentum is conserved. So that's easy. And is also expressed another way, can be expressed another way by saying that two translations commute. So UA1 times UA2 is simply UA1 plus A2, and that's the same as UA2 UA1, and this is what's called a abelian group. So that's the easy part. But how could we get the commutation relations involving mu nu? Well, the trick is to remember that this is a representation. So we first have to look what happens when we compose two Lorentz transformations. And that's easy to see, that if you first act with a pair A2, lambda 2, so we first do this on the vector, do this transformation, and then act with another transformation, lambda 1. Let me put a circle, meaning that I perform, this is a group operation. It's not simply a multiplication, as you will see in a moment. It means that I first act with this Poincaré transformation, and then with this, and the result is a third Lorentz Poincaré transformation with the following parameters: A2, lambda 1, lambda 2. So what this means is you first do this, you shift with this, and then when acting with another Lorentz transformation, the Lorentz transformation will act on this whole thing, and this is why you have this extra lambda 1 here. Now representation means, by definition, means that these U operators here should obey the same relation, or in other words, we require that UA1 lambda 1 times UA2 lambda 2 should be the same as u a1 plus lambda 1 a2 lambda 1 lambda 2. So this is the postulate, and the postulate comes from first of all observing that this is the composition law for the Poincare group, and secondly from insisting that that this map from the pair A lambda into to unitary operator in some Hilbert space be a representation. So this seen up here is just a special case of this relation if you put the lambdas equal to unity. Well, I don't want to go into this in too much detail. You can it is basically fairly elementary, but you can, for example, you now have to specialize a little bit these relations if you want now to calculate what the commutation relations are between p mu and m mu nu on the one hand, and m mu nu and m rho sigma on the other. So, for example, for instance, if you take, for instance, we take lambda 1, set this equal to lambda. We take lambda 2 equal to lambda to the minus 1. Of course, this should work for any pair, lambda 1, a1, lambda 1, a2, lambda 2. And we set a2 equal to, we call this a, and a1 equal to 0. And then this specializes to u lambda, u of a, and you can derive this from is u of lambda a. So the effect of conjugating one of these transformations with this representation of the Lorentz group, the effect of this is simply by rotating the parameter. Well, this is intuitively more or less obvious, but of course you can work it out in completely explicitly here. And now the trick is that you simply take this, you substitute these explicit expressions here and here, and then you choose the parameter to be small. Since we're just interested in the basic commutation relation, we choose these parameters to be small, and we just pick out the lowest non-trivial order coefficients, and then you find, for example, from this particular choice, it follows that you get the following relations. M rho sigma p mu is equal to I eta times eta mu rho sigma minus I eta mu sigma p rho. So maybe I should encircle this with colors. So we have to collect these relations because this is what we want to analyze. This, and we have this. And finally we have another one, namely m mu nu, m rho sigma. Well, this is of course the Minkowski metric. This is equal to I eta mu rho m mu sigma plus I eta mu sigma m mu rho minus I eta mu nu m rho sigma minus I eta rho sigma m mu nu. So what do these are the basic commutation relations that we now have to analyze. Now, what does this tell us? This is just another way, a more mathematical way of saying that the vector p mu really transforms as a 4-vector under Lorentz transformations. And in particular, we can now look at, well, what is this? Well, this is of course more general than the angular momentum algebra. But in particular, if you now choose these indices mu nu to be all space indices, then you recover from this. As a special case, you recover the angular momentum algebra. So in particular, it follows from this that Ji, Jj is I epsilon ijk, jk. H bar is always equal to 0, I told you. So this follows from this. I leave this as a little exercise to you. So my previous claim that this really is a rotation is now verified from these relations. Indeed, the Lorentz algebra contains, in algebraic sense, the algebra of angular momentum operators. And furthermore, we can check that, what is this? So this is just the usual vector notation. This you can substitute into here. And we see that this then will give 0, simply because if I take these indices to be space indices, and this is 0, they can never be equal here, so they're always 0. So I get 0 on the right-hand side. So this is angular momentum algebra, and furthermore it tells us that if I have this algebra, angular momentum is conserved. So these are special consequences of this algebra. Now what will I find if I take H with M I0? This is of course also contained in here, or here, rather. Well, I will find that this is different from 0, right? So this is different from 0. And that tells us that we cannot associate any conserved charges with the boost generators. That's why never anyone talks about the conserved boost quantum number, but the only conserved quantum numbers are momentum and angular momentum. So this is not conserved. So this is why this M, we never diagonalize M0I. So you just look at angular momentum. Where's the German? Did I get another 5 minutes? Because we started a little bit late. I'll just tell you what I'm going to do tomorrow. Tomorrow we'll start on time and we'll end on time. The next task will now be to classify representations by irreps. Now, how is this done in quantum mechanics? In the angular momentum algebra, you take J squared. This is a Casimir operator. Recall, I should say that SO3. Casimir J squared. That is the thing that labels the representation. Labels the irreducible representation, just the acronym. And then in order to label the states within the representation, we take, for example, J3, label the states. So we have to simply repeat this. We'll have to look for the Casimir operators, and this is a little exercise for next time. What are the Casimir operators? Operators for P. Well, for SO3 we have only one Casimir operator, but the Poincaré group is a bigger group, and therefore we expect there to be more Casimirs. And indeed, it turns out there's not just one, but there are two. And of course, they have to be relativistic invariant, because Casimir operators, how is it defined? It's an operator that commutes with all the generators of the algebra. Well, there are two. First one you all know, it's m squared, p nu. Well, that's the mass, of course. relativistic mass. But even not knowing that this is the mass, I can abstractly look at this algebra. I write down this operator, and then I simply check that it commutes with all the other, the mu nus and the p nus. For the p nus it's trivial, of course, but for the mu nus you have to calculate a little bit. So that's the first, that's the mass. And the second is the following one. It's called, doesn't have a name really. It's the following invariant, W mu, but what is W mu? W mu is defined as follows. It's 1/2 epsilon mu nu rho sigma m mu rho p sigma. So you see that this operator is quadratic, like the J squared. This operator is of fourth order in the Poincaré generators. And this thing is called Pauli-Lubanski vector. And as we will see tomorrow, this is related to mass, and this will be related to spin. So we already have the basic result, but we have to work it out a little more. The representations, the irreducible representations of the Poincaré group are labeled by mass and spin. And now you understand my claim initially, because if you think about a particle, then of course you think, how do I characterize the particle? It's characterized by its mass and its spin. In addition, you may have isospin, the flavor quantum numbers, etc., but that's not what we're talking about here. Once we have classified them, we can attach flavor and any kind of quantum number you might like to this particle. So thank you very much, and if you have questions, doesn't seem to be the case, so thank you very much. See you tomorrow.